Today we're going to be talking about the difference between linear dependence of a system versus linear independence of a system. Now, in order to talk about linear dependence or independence of a system, I'm going to be using matrices. So I'm going to assume that you're comfortable with those. So first things first, what does that even mean geometrically? Say we have a collection of vectors. Let's say this one's V. Let's say this one's U. And then notice I could have a third one here. And let's call that 2V. So what does it mean to be linear dependent or linear independent? Well, let's say I had a matrix that just had these two vectors, and so that they're different, let me call 2V W. So let's say I had a matrix with the vectors V and W. Well, if you look at this, all W is 2 times V. That's how I built it in the first place. And so this system right here would be linear dependent because I'm able to write one or more of these vectors as a multiple of the other. Another way of putting this is that if you have the matrix equation A, x vector equals the 0 vector, and if there's a way for you to do this other than just setting x to be all zeros for every component, then they're linear dependent. So an example with V and W here would be if I'm trying to solve the equation where A is my matrix here, and this is equal to 0, then I have the case where I could simply take V, let's say multiply it by 2, and subtract W. Since W is 2V, I've got 2V minus 2V right here, and so that's just going to come out to be 0. And so I can have my first variable x1 just be 2, and my second variable x2 be -1. And so there's some way to solve this equation other than just setting all the x's to 0. And so that's an example of linear dependence. Now, what if I just took these two guys, V and U? Well, in that case, if you look at these geometrically, U is not some scalar multiple of V because it doesn't lie on the same line that V does. Likewise, V is not some scalar multiple of U. So if this is my matrix A, then in this case, if I try to solve the equation AX equals 0, the only thing that works is doing 0 times V, the V vector, plus 0 times the U vector. This is the only solution. And it's called the trivial solution. You'll find that mathematicians tend to call two types of things trivial. One, things that are just too easy, and two, things that are too lazy to work on at the moment. So this is the only solution for this, and so we'd say they're linearly independent, and I'm just abbreviating this with LID. Likewise, this one would be linear dependent, because there's no way to write V as a multiple of U or U as a multiple of V. So another way of saying it is that the vectors are totally separate from each other. They're describing different parts of space, or different parts of a line, or different parts of a plane, or whatever is going on geometrically. Now, the last thing I want to point out here is that here I only had two vectors, and we would say the whole matrix A right here was linearly dependent. Here I had two vectors, and we said the whole matrix A was linearly independent. Well, what if I take all three vectors? What if I've got U, V, and W? And notice I'm not paying much attention to the ordering here. Make sure if you're given a problem, you keep the order, but for making up a problem, it doesn't really matter the order you put the vectors in. And now, this is my matrix A. And once again, I'm going to ask if I can solve the equation AX equals 0. Well, the thing is that even though V and U can't be written as multiples of each other, V and W can. And so I could simply do this. Put a 0 on the U, add 2V, and subtract W. Notice that'll work. Get rid of the u because it's not related to this, but then 2v minus w was the same way I got 0 here. And so if you look at this, x1 is 0, sure, but x2 is 2, and x3 is negative 1. And so it doesn't matter if some of your x's are 0. What matters is that if you're able to get any solution where at least one of your x's is not 0, and that gives you the 0 vector, then your whole matrix here is linearly dependent, because at least one of the vectors can be written as a multiple of the other. And so that's a general overview of linear dependence versus linear independence given a matrix.